Hidden in the permanently shadowed regions of the lunar South Pole lies a resource which is key to helping sustain humanity's expansion to the moon and outward: hydrogen. By using neutron spectroscopy, scientists made the incredible discovery that Earth's closest celestial neighbor contained water ice at its poles. The only question is, how much water ice is there, and what regions is it in exactly? While previous instruments did not have the resolution to tell us this, given the remarkable developments made in technology over the last few decades, the answer to that question can now come with small spacecraft. And that's exactly what the LunaH-Map CubeSat intends to do. Using a neutron spectrometer developed specifically for this mission, LunaH-Map aims to chart the distribution of hydrogen in Shackleton Crater, and thereby inform scientists and engineers on where we can find and harness any water ice that lies there. Hello, fellow space enthusiasts, and welcome to another episode of The Art of Space Engineering, the podcast which explores the engineering behind spacecraft and payloads and the lessons learned along the way. I'm your host, Sarah Rogers, and in this episode I had the great pleasure of talking to Dr. Craig Hardgrove, the principal investigator, or PI, of the LunaH-Map CubeSat. We chatted all about this tiny spacecraft and the science that it will do on the moon. In some recent exciting news, LunaH-Map was successfully delivered to NASA's Kennedy Space Center earlier this summer and is now sitting aboard its cozy new home on the SLS-1 rocket, which should launch later this year. So that's really, really exciting. Now, for those of you who are not familiar with LunaH-Map, it is a 6U CubeSat, which makes it just about as large as a shoebox, to give you some perspective on size. In order to complete the science objective, the spacecraft must fly at very low altitudes, about 8 to 20 kilometers, above the lunar surface, which is done with the help of ion propulsion and its guidance and navigation systems. From there, the rest of the spacecraft bus just helps support the science objective, and this includes two 6U-sized deployable solar panels, an electrical power subsystem, an onboard computer, and a deep space transceiver, which will communicate with NASA's Deep Space Network on X-band, Ka-band, S-band, and UHF frequencies. While the hardware came from many different places across the US, the spacecraft was integrated and tested entirely at ASU. So for me, it was always really cool to walk into the lobby of ICD-4, look into the clean rooms, and just see how the spacecraft was coming together over time. Now, given that and all of the excitement we've had around ASU with their delivery to NASA, it was really fun to talk to Craig a little bit about LunaH-Map and where things are now, and I know I certainly learned a lot about the spacecraft from it. So with that, I invite you to kick back, relax, and I hope you enjoy this conversation with Dr. Craig Hardgrove. I guess I'll start this off by, saying congratulations now that LunaH-Map is delivered and is officially integrated. So that's really, really cool.
Thank you. Yeah, it was a longish journey, but was happy to put LunaH-Map in the box and close the lid and start the next portion of her life.
So, and you guys flew it out there. It went to, because it's in Cape Canaveral, I think you said, right? So
yeah,
you had to go through the whole airport security adventure.
Yeah. It actually, it's weird to carry your spacecraft through the airport as carry-on, and we had to buy it its own airline ticket, so it had a seat on the flight.
Oh, interesting.
And I had to okay that with that was a strange call to American Airlines. I said, I want to buy two seats, and they said, oh, okay, typically they're used to somebody who, needs to occupy two seats for some reason. And they said, okay, is this for you? And I said, well, sort of. It's for a spacecraft. And I remember it's for a what? And so they said, okay. And they said, well, that's all right. You can do that as long as it fits these dimensions. And then they automatically booked it a return flight, and I said, no, we don't need a return flight. they were confused by that too, and so I had to book separate bookings. They figured it out. They were great, and then I had to get a TSA exemption, so we couldn't put it through X-ray. So I got in touch with the Phoenix Sky Harbor TSA folks, and it's funny, you just explain what you're doing, and everybody was very supportive. And it wasn't really that, I mean, by this point in the mission, we'd become pros at actually getting through TSA screening because all of our components had come from elsewhere in the country. So we had to fly them on airplanes and have this exemption. So it's like the Phoenix TSA folks probably knew us at this point. But we mentioned, you know, hey, we're flying the spacecraft out to Cape Canaveral, and they said, okay, you know, send us the paperwork and all the documentation and get a letter from NASA headquarters. And they sent us a certified letter that said we were exempt, and I put it in a binder and had my NASA badge with me and get to TSA screening with the spacecraft. And the only part that was weird was that they wanted to carry it, like they wanted to take it and carry it past the X-ray screening. And I asked, I was like, could you let me do that? And they said, no, absolutely not. And I was like, well, just so you know, that's a spacecraft that's going to the moon. So please, please, please be very careful with it as you're carrying it over there to the desk where you're going to swab it and all that stuff. And they said, oh, okay, that's the first time they'd heard of that. And when they got it over the desk, they're like, you're doing what now? and so I brought out, I always bring mission patch stickers. So I got out the mission patch stickers and told them what it was. And then they thought it was awesome. Like, and they, you know, did their tests and had to get a manager over, and he was just very excited about the whole thing and asked me what it was doing. And they were happy to be part of the first journey that the spacecraft took out of ASU. So it was the first flight was Phoenix to Orlando. So and then the flight attendants were the same way. So just very excited. They were telling the other flight attendants and the pilots, and people next to us were telling us stories about, you know, people they knew that worked for the space, you know, various space industries and contractors, and just were really excited about flying next to a spacecraft that's going to the moon. So overall, it was actually, you know, I thought it was maybe going to be really hard. It was fun, and you know, everybody's really supportive. Yeah, the hardest part about it was it's about 50 pounds when you put all the packaging and stuff in there.
Oh yeah.
And I had to, you know, I couldn't roll it because as the vibration frequencies are not great for rolling it. And so I had to carry the 50 pounds the entire way. So my arm for like the next 2 or 3 weeks was kind of sore. But you know, I had a death grip on that thing. I wasn't letting go. So
right. Yeah, it was weirdly easy to get like Phoenix through the TSA too. But we didn't have to do any other checks or anything. It just went through the X-ray, and like they didn't even ask us about it. They just like they just let it through.
Okay.
But then we bought the ground station hardware with us, and they wanted to look at that. Like they didn't care about the spacecraft. They wanted to look at the ground station hardware.
Yeah.
So that was interesting.
Yeah. Yeah. If you may not even need letters. I've heard, you know, you could just go and say, I think anyone can say they'd like to be X-ray exempt, and then you subject yourself to a significant amount of additional screening and the potential that they could deny you boarding for any, you know, various reasons. But you know, it's helpful if you have the letters to make sure everybody understands what it is. But yeah, I think it can go all sorts of ways. I know there was one, you know, we had to bring the neutron detector back and forth to Los Alamos a couple times for the calibration, and I was, you know, didn't have my Wheaties in the morning or something. I was feeling kind of grumpy, and the TSA agents were asking me questions, and they had like, all right, you're going to the additional screening, even though I had all the letters and everything. I just, you know, I was too grumpy that day. So.
Yeah. Did the spacecraft get like its own set of, you know, like airplane peanuts and stuff too?
I think I could have requested it, but I don't think they wound up giving us any airplane peanuts. No.
Okay.
Sadly.
Very cool. So to ask a little bit about integration and to, I guess, just compare it to what NanoRacks was like for us, how did that whole process go? So you get to Cape Canaveral, and then they integrate the spacecraft, but did you have to do any other checks like beforehand or after, or they just kind of boxed it all up and was like, here you go?
Yeah, for us, everything that we were going to do was predetermined prior to us arriving through many sets of reviews. So we proposed a set of activities that, you know, the SLS ground team would certify and verify that those were okay with their team. And so, you know, they knew exactly what we were going to do before we got there, and that was all we were allowed to do. They did allow us to take more photos than we had originally planned, which was nice. So I did get a set of you know, post-delivery pre-integration photos of the spacecraft that I wasn't sure we would be allowed to take, but they were fine with that when we actually got there. But yeah, we had a whole checklist, a set of measurements. You know, the dimensions were measured, the mass was measured prior to arrival, and then sent through a review board. And so all those things were there. They did their own measurements on the spacecraft prior to putting us in the dispenser. There's a set of separation switches that they wanted to make sure had appropriate, you know, clearances, and the lid would have sufficient clearances. And so once that was verified, they said, okay, you guys can put it in the box. They let us do all that. Terrifying. It was a terrifying set of like, I don't know how long, it probably took 15 minutes total, but like, you know, we didn't, the spacecraft being on a table is not a condition that we really ever had, like ready to put in another box. So we had a stage, you know, that you would mount it in, that you would basically, we had to use this T-slot that you'd put together, and then the spacecraft would get mounted into this structure, and you only ever have to touch the structure to rotate the spacecraft and put it on each axis. And the spacecraft is never sitting on the table, which is important if you have the solar arrays on, because you don't want those touching anything really. And you definitely don't want to put the spacecraft down on one of the array panels, which turned out to be the biggest fear during these, you know, 10 minutes. So yeah, we had to take it out of the Pelican case and rest it. So this is just the spacecraft free flying as it's going to be in space, right? So the spacecraft has no structure around it. We have to take it by hand out of the box and then rest it on the table. And we didn't necessarily, we wanted to put it on the side. You can't rest it on the propulsion system is on the bottom side, which would be kind of the bottom of the cereal box, if you want to think about it that way. And we couldn't rest it on the bottom of the cereal box because we had a remove before flight switch that was pushing out and but the spacecraft would fall over. And so we had to put it on its side, which means we had to, the solar panels are on the sides of the cereal box. So that meant we had to rest it on carefully on two parallel bars of T-slot just on the edges of the solar panels. Keeping in mind that if it slid off of that T-slot in either direction, you know, the mission is probably over, right? Because we've cracked solar panels or something. So yeah, I was a nervous wreck, like having to rest it on these two bars and then do our inspections, remove one of the remove before flight suite before we could tip it back up onto the bottom of the cereal box. And then it's, you know, still nerve wracking because it's just sitting there, which is just weird because it hasn't ever done that. And then we took more pictures. The SLS folks measured it, and then yeah, they said put it in the box. In which case, then we picked it up again, and that part was okay. You just kind of slid it into the box, and we'd done that before at ASU. So we'd actually done this whole process. It was just as nerve wracking and terrifying. Once or twice before, they sent us a dummy integrator, like the dispenser, and we were able to test the integration and made sure we weren't hitting all the clearances. And yeah, we slid into the box just fine. They did another set of measurements, made sure that they could, they have a cable that they plug in from their avionics unit that'll tell the box to open when we're ready to deploy. So they wanted to make sure that those clearances looked good before we closed the lid. They did that. Then they told us, okay, you can close the lid. It was very hard to close the lid. Like you had to push with a bit more force than you'd want to. Not because the spacecraft was in the way. It's just the way that the mechanism works to open the door. And so you kind of push down and then it locks. And I think we were maybe the fourth CubeSat to integrate, and it became this 3-day-long tradition where everybody would round of applause when you hear the locking mechanism latch on the CubeSat dispenser door close. So we get this nice round of applause, and
Oh, that's awesome.
and then you hand it over to SLS. So the integrator folks take it, they make a mass measurement, they do some more measurements on the dispenser box with the lid closed, and then it goes and sits on a table, and it waits for the SLS EGS, Exploration Ground Systems personnel, to take it and put it into the Orion stage adapter, which is where all of the CubeSats will live until they're deployed. And that's that round ring that we're all mounted in, it sits right underneath the Orion capsule. So after the Orion capsule deploys and maneuvers, does its lunar flyby, all our CubeSats deploy in this ring. And so we're currently, LunaH-Map is in there with about 10 other CubeSats or so, at Kennedy Space Center. So
Very cool. Yeah, I remember when they were fitting like Phoenix and the NanoRacks deployer, and they kind of move it around to make sure tolerances are good. And like we were so nervous because we did measurements and everything, but tolerances are always and we weren't entirely sure that we were going to fit. We thought we might be like slightly too big for it. So yeah, that was it's nice that you got to verify it beforehand.
We were lucky we had that dispenser to check with. So everything worked out. So yeah, it's all nerve-wracking though. I mean, and all of it, even if you've done it before, it's like,
oh yeah, for sure. How does so for the remove before flight switches, is that kind of, because for NanoRacks, we had to put like little roller switches on the rails of the CubeSat. And so the deployer would press those down, and then those were connected to our battery inhibits, and then that prevented any power from being applied to the rest of the spacecraft. Was it kind of similar for you guys, or do they have a different mechanism for the SLS?
I don't think there was anything attached to the rollers. So there's a plate on the door and then a plate on the back side, the pusher plate that pushes us out of the box. Mm-hmm. And so we have the remove before flight switches activate the spacecraft. So we had to remove the bottom one, and since we still had the top one on, the spacecraft didn't boot. And then we were able to slide the spacecraft into the dispenser, wait until the bottom pusher plate separation switch engaged, then we could remove the top one, and then you could close the door, and now you have both separation switches engaged, and the spacecraft can't boot unless you apply external power or something like that. But we can't do that. So there's no way it's booting until both of those separation switches are disengaged. So after the pusher plate pushes us out and we separate, and then there's a 15-second timer so that we can just physically clear the Orion stage adapter, and then the spacecraft powers on. The burn wire releases the solar rays. So.
Okay.
Point at the sun and phone home. That's
yeah. You can hear it beep.
Yeah, hope so. Yeah.
Okay. Because that was going to be one of my other questions, was if you guys got to do any other like checks before launch, because I know I think for spacecraft they'll do at least some, but yeah, we were the same way. It was like we put it in the deployer, and then it sat on the ISS for months until it actually deployed, and then we were like, well, is it going to work? I guess we'll find out. So
yeah, we did a lot of testing. So I mean, everything on that spacecraft has been tested, and we've tried to test it in as flight-like a way as possible. The hardest thing, surprisingly, to get a test accomplished was our radio antennas. So we did wind up testing those using antenna hats. Just little caps that you put over the antennas so that you don't broadcast radio waves out into the lab. And so it turned out that was like, we didn't have a whole lot of experienced RF engineers on staff. So we had to, bring somebody in from the outside to help us structure the test, make sure we had the right success criteria. But yeah, we were able to verify everything down to both pair. We have 2 antennas, 2 transmit, 2 receive on either side. We verified that they work. The propulsion system was tested with our an engineering model of our flight system, so the flight computer and power system. So you have to test it in a vacuum chamber, and so we weren't able to bring the entire spacecraft into the vacuum chamber, nor would we necessarily want to, because the propulsion system uses iodine, and so things get a little bit greasy in there with the iodine, and we just didn't want to subject the spacecraft. It's a function of the fact that the iodine's trapped in the TVAC chamber, and so it has nowhere to go. It's just deposits on stuff in the chamber. In space, we shouldn't have that problem. It's going to go out into space, and so
Gotcha.
It becomes a dirty TVAC chamber with these iodine systems. So, but yeah, we were able to test the propulsion system for a few hundred hours or more.
Oh wow!
So,
did you guys do that at ASU, or was that
no?
At
No, I wouldn't subject our thermal vacuum chamber to the iodine, but the company that manufactures these propulsion systems has a number of thermal vacuum chambers that are set up with gas and pumps to remove iodine from the TVAC chambers themselves, and yeah, they did those tests there. So we took our hardware to their facility and did the test there with our propulsion system. So.
Gotcha.
So yeah, that was tested. The neutron detector was thoroughly tested. Like I said, we went to Los Alamos to do a calibration. I probably used it too much at ASU.
Use it too much.
I could not get enough measurements, before you could ask our team. I mean, I was just coming up with all sorts of measurements that, I wanted to make. So we hundreds and hundreds of hours of measurements with that system. And, the problem is on Earth, we have a kind of a weak neutron source that I have to use. And so to get a good signal equivalent to what we'd see on the moon, you kind of have to keep the instrument on for many hours. And so we really put it through its paces, temperature cycling and all that. So I feel pretty confident in the subsystems themselves. It's, the integrated system and any unexpected things that we, might run into, which I'm sure there will be. So, but yeah, everything was tested. Thank goodness.
So what are you guys working on now? Are you just preparing for mission operations, or do you actually get a break after, all these years of working on it?
No, there's no rest for the weary. It's we're our operations team is planning a series of readiness reviews and tests. And so we're starting out with some rehearsal simulations, which will set the stage for the later operational readiness tests, which will simulate mission scenarios, various elements of mission scenarios. And the purpose of the rehearsals is to get staff, operations staff, trained in the procedures, make sure that we know what systems, what ground systems we're going to use, what tools are on their laptops, what the telemetry looks like, what tool they might use to process it, those types of things. And then later, as we get closer to launch, the operational readiness tests will actually simulate using actual data from either the flight spacecraft that we collected before we send it off, or from our FlatSat, real missions scenarios. So we'll say, okay, this is post-deployment to 72 hours, and we're just going to play a tape, the telemetry, and we're going to feed that through the ground system, give that to the operators, and see what they do. And you can inject errors and things like that to see how we would recover from a certain scenario. And most of our trainings and tests are going to focus on deployment to 72 hours up to launch. But yeah, that's primarily, there'll be at least 2 or 3 operational readiness tests, and then a flight readiness review. SLS has a few reviews they want to go over with us, but they mostly know the answers to the questions already. They just want to verify that nothing's changed. And yeah, then I don't even know if I get to go to launch or not, but I'm hoping I can. So, but yeah, operations preparedness and readiness is primarily what we're working on now. The other element of it is the navigation team is working up the navigation solutions based on predicted launch dates. So the last official launch date that we had is November 23rd of this year, 2021. And so we're looking at refining the exact trajectory that we would take if that were the launch date. And that feeds through into when we would request communications passes, how often, when we would need to ask for those along the way throughout the mission. And we'll use those to plan our readiness tests. So the navigation team is in the loop with our mission operations team. And so as we execute a propulsive maneuver, we'll want to check back in with the navigation team when we get data to say, are we on track? Do we need to change, course correct, those types of things. And they'll provide us with a new orbit determination that we uplink to the spacecraft on the next comms pass. So those are the other types of activities that we're talking with the navigation teams to define the products that they're going to deliver to us and the ones that we're going to deliver to them, so that we make sure that we're talking the same language when we operate. And so, yeah, it doesn't stop. Unfortunately, we don't get a break. It's a lot of work. Fortunately, I don't think we're launching in November, so it's got a little bit more time.
Mm-hmm. So I guess to kind of go off of that, because I know like the SLS has moved quite a bit to put it briefly. So when you guys when you started defining the mission and then doing all of your trades, navigation included, have the trajectory predictions like changed a lot? Because the SLS is still planning to do, I guess, the same thing. I'm not sure how much the trajectories change based on how the launch date is moving. So like, did you guys have to, put in maybe more margin than you would have otherwise because of that?
Yeah, so because we're a low thrust mission, so our propulsion system is like the size of a tissue box. And so we get less than a millinewton of thrust from the system, and so our propulsive maneuvers are sometimes days long, and we can't do a lunar orbit insertion right away. If we could, then the launch date wouldn't matter as much. But because we have this low thrust trajectory, we are subject to the Earth, Moon, Sun position at the day of launch. So depending on the configuration of the Earth, Moon, Sun, we're either in a good configuration or a bad configuration, and that translates to shaving 6 months off our total mission duration or more. And so you can predict, obviously, it goes in a cycle. Once every 2 weeks, it goes from shaving off 6 months or adding 6 months, either way, kind of like that. So we know the behavior, but until we can put a date on a calendar, it doesn't help us. We have to have a specific date to within 2 weeks to really be able to plan anything more granular than to within 6 months. So the slips have been frustrating for sure in terms of planning our phase E and phase F. But as it's turned out in the course of the mission development, we really the slips were very serendipitous for our mission development. A lot of the technologies we needed, we hit issues along the way that we needed all that time. So it's not like we could have delivered if SLS launched in 2017, which is when we originally thought it was launching. It wasn't happening. Various things were not working at that point for us. So,
gotcha. That's really interesting. Because I guess I don't know. I guess that's the first mission I've heard of that's really like that. Because I mean, a lot of like the Mars missions, it's like, okay, you have a certain window every few years to actually launch, and then this is kind of what it looks like. And I think even for like Europa Clipper, based on what launch vehicle they chose, they had 2 trajectories already defined, and so it was just a matter of which one we'd go with. So that's really interesting.
The joys of being the primary payload. Yes. Yeah. If you're the reason you're going to Mars or Europa or the moon, you get to pick your launch date and trajectory. We have zero input into this process on SLS. So Orion decides when they want to launch, and yeah, it's their show. We're just riding along. So,
gotcha.
But yeah, that's one of the things that I think makes it really tough to do a science mission. I mean, if you're doing a science mission to collect important, meaningful science data about the moon, you want to give yourself the best chance you can to do that. And so you want to pick a favorable launch date if you could, but none of the dates that are selected, they add to our overall mission duration. It doesn't influence in a meaningful way the overall science data that we would get back. So it just impacts the overall cruise and transition duration of the mission, which is really more of a mission assurance and risk posture than anything else, right? It's like, are we okay with operating the spacecraft for an additional 6 months in space? And we're okay with that. Yeah, it's okay. But with the levels of mission assurance and risk that are on a mission like ours, yeah, that's okay. We're okay with that. So
gotcha. So you guys probably had to prove that your components would last, like twice the mission lifetime or something like that, with like worst case analyses, that kind of thing.
We didn't have to. So we did, but we didn't have to on this mission. So the actual standards for the call that we proposed for LunaH-Map, which is not the case for future deep space SmallSat missions, it was a requirements for high altitude ballooning. So we're issued a grant, and LunaH-Map was developed under a grant as opposed to a contract. Contract, there's a specific deliverable. You will deliver a spacecraft. Obviously, we have delivered LunaH-Map physically, but technically with a grant, hardware is not often a part of the requirement. So it was structured as a research grant, really. And so we implemented it as a spacecraft mission. We held reviews. We looked at the components and the total ionizing dose that they were capable, that had been tested to. And we looked at what reasonable radiation environments we might expect at the moon. And yes, to answer your question, yes, we can survive if we had an additional 6 months. But just maybe it's important to me, maybe not many other people, but there was no requirement that we did that. So we just had to do what we felt was best for the mission within the restrictions that we had, from budget and schedule and all those other things that come into play, personnel. So yeah, I mean that tends to be like, that's a little microcosm of the mission, but I mean that was one of the main challenges for executing a mission like this is, and it enabled the mission too. So if we had to be subject to, like you mentioned, proving anything, so, usually that costs a lot of money, to prove something to within a certain % assurance. That requires a set of models or tests, and that requires money and time and people. And we did a lot of tests. We tested all the hardware. We tested many of the critical mission scenarios. We did not test everything. We just couldn't. And so there are things you would do on a big mission that we just didn't. So we tested the things we felt we had to, and we felt were critical to the mission success. And things like the total ionizing dose and radiation hardness of various components. We have rad hard parts on the critical components that can't fail, but not all of it is rad hard parts. So,
gotcha. But
it didn't have to go through a review board that looked at all the schematics and all this stuff and tells us we need to change X, Y, and Z. None of that happened. I mean, we had a PDR, a CDR, we had a requirements review. We held those, but we the project held those because we wanted to.
Mm-hmm.
We weren't required to hold them, and they weren't gate reviews in the traditional mission sense, where if the review board doesn't like what it hears, you could be canceled, or you don't go through the gate. Like we took the recommendations that we got from the review board and implemented the ones that we could, but we wanted to hear that feedback. We weren't able to implement some of the recommendations from the review boards. So
Gotcha.
Yeah, it's a totally different mission structure than most large NASA missions. So.
Yeah, I didn't think of it that way. It's funny because I mean, for Phoenix, when we were given the grant from NASA, like they didn't tell us, you have to do all these analyses or anything. It was just kind of like our goal was just to deliver a spacecraft, basically. We tried to make it as functional as possible, but we didn't have people telling us what analyses to do. We just we did things that we had the time for. And it's so different for missions like ETHEMIS, being a payload on Europa Clipper. Like we have to do all of these radiation tests and like even magnetics testing since the spacecraft's going out to near Jupiter. We have to do all of that. And that was like our radiation analyses were done by Ball. So we had to coordinate with them and get all of our materials and everything approved with JPL. And so we had to go through all of those checks because like our stakeholder is
right.
JPL, and we have to make sure that we're compatible with their spacecraft. So that's
right.
That's a really interesting dichotomy that I completely forgot about working on on instruments. So
I should say there was, so this one of the important stakeholders in our process is the SLS team. And they imposed a set of requirements that we had to meet. So we had a safety engineer, we had a materials sheet, a list of all the materials in the spacecraft that were submitted. We did a structural analysis, finite element analysis of the spacecraft. We went through thermal vac. We did all the requirements. Those were required from SLS, but also for ourselves to make sure that the spacecraft could survive and operate in the expected environment. But yeah, the SLS did impose a set of strict requirements on us. But from their perspective, it wasn't a mission assurance. Right, they were interested mainly in a safety point of view. From is this spacecraft okay to put on a rocket? So their questions were: are there electrical issues? Are there materials issues? Is there a mass issue potentially? Are your batteries? Our batteries came directly from SLS. They told us what batteries to use and gave us the batteries that they certified. So they wanted to make sure that those were all approved. So there was a set of approvals in that sense, but the mission assurance type requirements came from us internally as opposed to coming from something external. Like in the case of ETHEMIS, those are going to come from JPL or somebody, but for us, we define those.
Mm-hmm. Yeah, we had something similar for nanoracks, like them making sure that we fit into their deployer and that all of our like antennas, weren't only like they had some sort of secondary deployment mechanism that wasn't just the deployer pod, electrical issues, things like that. So
yeah.
So one thing I was curious to ask about was kind of the start of LunaMap and more of the project definition phase, because one of the hardest parts for us in working on Phoenix was just defining like what our requirements and scope were supposed to be. Because I mean, we had never done anything like this before. And we weren't really sure like what had to be done at a minimum. What's the difference between having your minimum objectives and then things that are nice to add on. And I feel like it's so much harder to control the scope of that for science-based missions because there's so much that you want to do and you want to make sure that you can get the best science that you're going to get. So I was curious to ask if the mission like scope and what you guys wanted to achieve was always clear to you guys when you started out, or did it take a while to kind of arrive at, I guess, what LunaMap is now? And yeah.
Yeah, I think we've been somewhat fortunate, and it's probably because we don't have a camera. And I say that we tried to put a camera on LunaMap for a while. There were, I think even at PDR, we were toying with putting a camera on LunaMap. And we want, our star tracker can take images. So that's where we ended up, is we do have a camera. It's just our star tracker, and we would have to put it in image mode. I'm only starting with that because I think if you have a camera or some kind of system that requires some pointing, that's where you run into scope creep in terms of the science. So for our mission, we have one instrument, and it's a neutron detector. You can think of it kind of like a Geiger counter, right? So you're just counting neutrons that are at that altitude above the moon, and they come from the lunar surface. And so if you change the orientation of the detector, the difference in count rates will change a bit, but it goes like cosine theta. So it's not really that much. Like, it's a fraction of a percent if you rotate just by a degree or so. So it doesn't, as long as you have knowledge of your pointing, you're okay. You can make a correction based on the small angles for how many neutrons could be hitting the front surface of the sensor. So we don't really, other than just flying over the South Pole with the detector on, we're not a targeted mission, right? There are places at the South Pole that we are more interested in, but we're not going to maneuver the spacecraft specifically to get those places. We're going to kind of design the science orbit so that it gets good measurements over those, but we're not going to really actively control the spacecraft pointing or orbit in such a way that we fly over specific zones other than the South Pole. And so I'll back up and say, so the overall mission concept came from neutron detectors and neutron maps of the moon have been made before. There have been 2 instruments that have been sent to the moon to make neutron maps, and the neutron map can be converted to a hydrogen map, and that tells you about how much water really is at the surface. Water ice is bound up in the top meter of the moon's rocks and soils, and that got there from passing asteroids and comets, and perhaps there's endogenic, like there's water somewhere with volcanic eruptions on the moon. We're not really sure how to account for all the water that they know is there from a lot of the missions that have been sent to the moon. But these neutron maps are really good because they integrate down to about a meter into the soil. And so every other technique is just sensitive to like the optical surface, a micron or so. And so this tells you about the bulk, but they're spatially not very fine. So they're a coarse spatial measurement. The previous instruments that have been sent make maps that are on the scale of hundreds of square kilometers, 50 to hundreds of square kilometers, usually 100 to 150. Very, very large patches of ground. And so you can tell that the poles are enriched in hydrated stuff and likely ice, but you can't really tell exactly where it is. And it looks like it might be concentrated in these regions of permanent shadow. There are these areas on the South and North Pole that never see sunlight. But you can't really be sure with the neutron detector. The pixel is too broad. And so you say, well, it could be all in the permanently shadowed crater. Maybe there's some hydrated material outside the permanently shadowed crater. We don't know. And so the whole idea with LunaMap was just to take a neutron sensor and fly as low as safely possible over the South Pole and make a map that's at a resolution that's smaller than the permanently shadowed regions at the South Pole. So you can look at a map and say, all right, there's permanently shadowed craters that are like 40 to 50 kilometers in diameter. And you take that and say, all right, well, I'd like to resolve that. And so there's lot of work that's been done to define what the spatial footprint of a neutron detector from orbit is. It's about 1.5 times your orbital altitude. And so if you could fly over the south pole of the moon at 10 kilometers, you might have a pixel that's on the order of about 15 square kilometers. And you could put several 15 square kilometer pixels inside a 50 kilometer diameter crater. And that's literally where the requirement came from. That was it. It's just, okay, so we fly, that's how you define the altitude. Then you say we need a neutron sensor, and then you say, okay, well, how long do we need to orbit to make a meaningful measurement? All we're doing is counting neutrons. And so if you count them enough, you need to get to a certain level of precision. So in counting experiments like these, the uncertainty goes like root number of counts. So you can say, all right, I can predict using a set of models how many counts I'm going to get from potential hydrated spots that are in craters and dry spots. And I can look at my orbital velocity, how fast am I flying over the South Pole? About 2 kilometers a second. So 2 kilometers a second, how many counts per second? Something like 40 maybe. And now I can start to say, all right, what kind of uncertainty do I want to achieve? And that's how you build up we have a 2-month science orbit. And we say, okay, we want to be able to resolve about 500 to 600 parts per million within a 20 square kilometer region at the pole. And that's a place where we pass over basically every orbit. And so to do that, you need about 2 months in orbit. That's how the science requirement came about. And so it's really an altitude requirement combined with a duration requirement. So how long are we in orbit? But and then you need a certain sensitivity on the detector because you need to make sure you count those neutrons. You get the count rates that you expected. Another super fun part of this project is that we had to build a completely new planetary science neutron detector in addition to building the spacecraft. So that instrument had to be invented as part of this project. There was no off-the-shelf deep space ready neutron sensor that had sufficient spatial coverage on the CubeSat that would get us the count rates in 2 months that we needed. So that was what we proposed, was to build one. And so that's what we did as part of this, which made this, very, very, I say fun and challenging, I guess. But yeah, it got done. So.
Was the instrument built at ASU too, or did you also have to just buy parts from other places around
It was a combination of a vendor. So there's a company in Boston, Massachusetts, they traditionally make sensor heads for the Department of Defense, has a lot of use for radiation sensors. And so they had a lot of experience making the sensor head portion of the instrument. And so we worked with them to define the sensor array. So in this case, we needed many sensor heads to line this face of the CubeSat. And then also the associated, chassis, electronics, and analog circuitry that would need to go in to the instrument. So it was a combination of ASU personnel and this company. It's not necessarily what they have done in the past, but we were able to work with them and have some engineers on our side that have worked with, Phil Christensen's team and others to help define the instrument requirements and how it would function. So yeah, it's really kind of a partnership between the two of us on the instrument.
Gotcha. That's really cool. So I guess to kind of go into that a little bit more too, how exactly does the neutron spectrometer take measurements? Like, is it shooting something at the surface of the moon, or is it?
No. It's just totally passive.
Okay.
And it works the same way not entirely the same way. The tried and true neutron detector in planetary science is a helium-3 tube, which is it's a gas proportional counter. It's a cylinder. It's filled with helium-3 gas. You have a wire that goes through the gas, and you charge the wire, and a neutron interacts in the gas, in the helium-3 gas, and it creates an alpha particle and a triton, and those shoot through the gas and ionize it, and they deposit charge on that wire proportional to the energy of that neutron hitting the helium-3 atom reaction. And so all you see is these pulses, and the pulses tell you there was a neutron that interacted with the helium-3. And you don't know anything else about the neutron other than there was a neutron. And so that's the way it's traditionally done. Those are cylinders, and we just couldn't fit enough of them into the CubeSat. They also they're not equally sensitive along each axis of the cylinder. And so it's not like we could get an efficient detector lining the CubeSat. So it's a great detector, but we couldn't get enough of them squeezed into the CubeSat to really get the count rates that we needed.
Okay.
So we went with a different type of detector, which is called a scintillator. They've flown before. There was one on a mission to Mercury, the messenger mission.
Okay.
And so those work, and ours is no different. There's it's called an opasolite. So these are crystals that are actually grown. They're inorganic crystals that are grown in a big vat. And they have a certain chemistry that allows anytime a gamma ray or a neutron passes through the crystal, and in the case of a neutron, it actually gets absorbed by a lithium atom in the crystal. There's another one of these reactions. And in a scintillator, those reactions produce light instead of, like I mentioned, the other one's like a charged thing, like this charged, triton alpha particle. In this case, particles are created, but also there's a light flash. And so all you do is you attach a photomultiplier tube, like a light catcher, basically to the back of the crystal, and it reads out all the light flashes. And so you see the amplitudes of the light flashes instead of amplitudes of the charges that's on it. And so this crystal we line the CubeSat face with 8 of these crystals. You can only grow them so big. And so that's why we couldn't just make a huge one. So we had to grow them only about, 2 by 4 centimeters each. And so you could line the CubeSat with about 8 of them. And then you gang them together in electrons. Anyway, so you read out these light pulses, and the light pulse is characteristic of a neutron or a gamma ray energy. So the amplitude of the light pulse tells you what type of particle was interacting in the scintillator. And so it's just, the hard part is getting all that to package together so it's ready to survive, launch, and then getting all the electronics and signal processing to take that little mini light pulse. Even after it goes through the photomultiplier tube, it's still a pretty tiny pulse. And so you have to amplify it, shape it, and then do some processing on it to say if it's a gamma ray or a neutron, and what are the properties of that gamma ray or neutron. So we had to develop, all the flight software that does that processing. I didn't appreciate how much work that was at the beginning of this whole endeavor. I was like, we'll build an instrument, whatever. That whole part was really tough to structure all that. But anyway, that's how hopefully, does that explain kind of how it works?
Yeah.
Yeah, and the neutrons are just, so everything in the solar system is bathed in galactic cosmic rays. Here on Earth, we're lucky that we have this thick atmosphere to protect us. And so we don't get a whole lot hitting us down here on the surface of the Earth, but the moon doesn't have an atmosphere. So a lot of these high energy galactic cosmic rays hit the surface of the moon, and they interact at the atomic level. And so they interact with just any nucleus in the lunar rocks and dirt, and they make high energy neutrons. They generate high energy neutrons. And the physics of this whole thing is just kind of billiard ball mechanics. Like a high energy neutron, you can think of it like a ping pong ball. It's bouncing around in the lunar rocks. If you have another ping pong ball in the lunar rocks, anytime it collides with another ping pong ball, it loses about half its energy. Every other atom in the periodic table looks like a bowling ball to a neutron. And so hydrogen is the most efficient moderator of neutron energies. And so all you have to do is just count the neutrons in a certain energy range. And if you see more or less, it tells you about how much hydrogen is in that portion of the moon that those neutrons are leaking out from. So it's a completely passive technique. And if you ever look up if you look up water on the moon, you should see a map that was made with a neutron detector of the global distribution of water at the moon. There's a map of Mars that was made the same way with a neutron detector. the scale on that map is like 500 square kilometers per pixel, but the poles stick out. You can really see the ice caps. They've made maps of Ceres in the asteroid belt, of Vesta with a neutron detector. So you see like Ceres is this ice body. It's like 60% ice. The map looks really cool. And the North Pole of Mercury was mapped with a neutron detector. And so it's a common technique. It's just not known for making high resolution maps of anything. So it's, these broad kind of regional scale, planetary scale maps. So this is one of the, LunaH-Maps for the first time. We're going to try to get 10 to 15 to 20, kilometers with it. But anyway, that's the how it sort of came together.
And so for the detector, like the crystals, so basically every pixel, like light passes through like the pixels in the detector. Or are they pixels, or am I just too used to cameras?
Too used to cameras.
Okay.
It's just a one solid. So we have it's an array, but it's only an array because we need more surface area. So it's just, you could think of it as one big sensor. And so within the crystal, you just count neutrons that interact in that crystal. So a neutron interacts in the crystal with a light flash, and all you do is count it. And so as we're flying over the moon, we're just making you think of it as a time series of counts, just counts over in time. And so it's, squiggly plot, right? And so you're just making a map and you say, okay, over this patch of ground, I saw this many counts per second. And if you just divide the moon up into, 5 degree by 5 degree bins or something like that, longitude, latitude bins, you say, okay, throw all your counts into these latitude, longitude buckets. And when I was over this this grid, I saw this many counts. This grid, I saw this many counts. And then as you orbit, you just put the counts that you saw into those buckets, and then you have a map. And as long as you can interpret those counts with respect to one another, you can make a map of hydrogen. So it's not a camera in any way. Yeah.
Gotcha. Oh, that's really cool. It's also a lot more complex than I thought it was going to be.
In some sense, I feel like it's less complex than a camera, but maybe it is more. I mean, the physics of it are potentially more complex. I'm not sure, but we don't get like pretty pictures necessarily with our instruments. So.
Continuing on the payload side of things, so you mentioned you had to take it to Los Alamos for calibration. How exactly does calibration work for an instrument like that?
Yeah, so we did that for a few reasons. One is to get the spatial response of the instrument. So we're flying pretty low, and you don't tend to think of these instruments as having any directionality to them, but they kind of do. And ours is rectangular shaped, so we've got a little bit different sensitivities in different directions. We also have a shielding material on the front, not on the back. So one way, if you have a neutron source, like a piece of californium or something, you can put the detector on a table and put the californium a certain distance away, and you can measure neutrons. But we want to know what the absolute efficiency is of the detector. We want to know for X number of neutrons coming out of this source, we want to know how many neutrons do we detect. And so we need to do that very carefully, because if you put it on like a wood table, for example, there's some uncharacterized amount of hydrogen in the wood that's going to moderate the neutrons coming out of the californium. And now the number that we detect is different than what actually came out of the californium. And so we want a very clean measurement where we know very accurately the strength of the source, and we know very accurately what's happening in the space around the detector. And Los Alamos has done these types of calibrations before for previous neutron instruments that have been sent to Mars and the moon. And so they have this basically just a big open room. And then they have a strong piece of californium that shoots up out of the ground, and it goes up into the middle of the room. So there's a big platform in the middle of the room that you can put your experiment on, in our case, our spacecraft and detector. And then you can move it different distances away from the source that comes up from the ground. And everybody it's a big bunker, so you have to kind of evacuate when the thing comes up. It's a really strong source. And so it's a big, maybe 50 to 75 feet, something on either side, tall ceilings. And so the neutrons that are hitting the detector are only interacting with the scaffolding that's maybe around it and then hitting your detector. And Los Alamos has a model of the scaffolding and the walls. And so they know what's happening with the neutrons that are interacting with all that material. And so you can use that to just say, okay, I know the strength of this source. I know what's scattering, what's happening in this room, even though it's minimal. And then you can see how many you actually count and compare that to the known. So that's an important measurement to make. And we did this at ASU too, basically did the table experiment that I mentioned to you. And it turns out it's not too bad. Like you don't necessarily need a huge room, but it's a nice comforting thing to do the calibration at a place that most of these bigger missions had done it. The other reason is you can rotate the instrument on a stage like this, and so you can see what the spatial response function is of the detector as you're rotating the plane of the detector face away from the source. And so you can build up this function. And so as we're flying over the moon, we'll say, okay, now I know that what the neutrons we counted only came from this swath of the ground in X, Y directions. And so those are the reasons to do that calibration. It's not like an image calibration, it's somewhat different. But
Is there a reason why californium is used in particular, or is it just because it's a really strong source and that's just what they wanted to use?
No, people can use americium, beryllium. These are just kind of common neutron sources that are used. I'm sure there are others that I'm not a nuclear physicist necessarily, so I don't know all the types, but the half-life on californium is, I think, 3-ish years or something like that, a little less than 3 years. So it's pretty good, and it gets you, the energy. One of the reasons it's good for us is the energy range is pretty wide. It's lower. It's peaked around 2 MeV. The neutrons we want to detect are low energies. So 6 orders of magnitude lower. So we actually had to moderate. There are these big moderating spheres that are big pieces of plastic that you can put over the californium source that have hydrogen in them. It's been characterized, but so that they moderate all the energy, the neutrons that are coming off the source. And our detector can see more neutrons because the ones that come off the californium are too high energy for us to see that many of. And so that's mainly why we chose it. There are other high energy neutron sources that we just ruled out because they're already higher energy than californium. So, yeah.
Right. That's really cool. It's also very different than I guess any kind of calibration that I'm used to. So
it's really, I'm always jealous of the imaging and spectroscopy folks, because you can't really ever get with a neutron instrument the exact measurement that we're going to make. And I know you probably can't do that with imaging or spectrometers too, but we can't get galactic cosmic rays here. That's going to be our source of neutrons at the moon. I can't just have those and subject those to the detector right now. So you have to simulate it. You have to go to do this test where we're using a strong californium source. But even that isn't really what we're going to see when we go into space. As opposed to, I feel we know the solar emission spectrum, the sun is shining, you could go outside, it's the same sun, it's different because of the atmosphere, but I'm sure I'm probably making people who do that science mad, but I definitely feel I wish I had a galactic cosmic ray source or something like that to use very carefully.
Yeah.
I don't want to use it for good, not bad.
Yeah. I mean, that's what we'll tell people. Yeah.
To calibrate our planetary neutron sensors. That's what I want.
Yeah, because I mean, we just use, for PhilScope, we just use black bodies for all of our measurements. And when we're doing TVAC, the black body is set to the temperature of whatever of the surface that we'll be looking at. And we can get all of the essentially values that we need to kind of validate our calibration process, like emissivities. We can get all of that from just that data, and it's fairly accurate. So well, TVAC is that's why TVAC is the most important test for like the kind of infrared imaging systems that Phil's group does, is because that's where they get all of the unknowns about the instrument, and can create like an instrument response function that kind of like actually help us calibrate the instrument when it's in orbit.
Yeah.
So
yeah, I think
very different.
Photons are a little bit more well behaved. I'm going to go out on a limb and just say that. I'm not sure if that's true, but I feel like, you know, neutrons are, at least high energy neutrons, are always just going through stuff. You know, they're traveling through all sorts of materials, and, you know, their probability of interacting is, you know, proportional to their mean free path within whatever material they're going through. So it's like, it's kind of statistical what they're going to do. And so it's, I know photons are probably all statistical too, but I feel like it's, you know, you can't account for like the neutrons flying through the chamber that you put them in. Like, it's just, you can't build a big enough chamber, but maybe you can. I just don't have that chamber. The other thing that is nice for us is because there are these other missions that have gone to the moon and to other planets that are asteroids that have no atmosphere, there's a really well-established relationship between epithermal, which is the energy range of the neutrons we're going to measure. They're just called epithermals. Thermals are like room temperature neutrons. Basically, that's where the name comes from. Those are the low energy ones. Epithermals are higher than that. So we're going to measure those. There's a relationship between those and the hydrogen content of dry airless body regolith. And so we don't really need to have an absolute calibration. We really just need the instrument to be consistent between one measurement to the next. So we need to measure you. So if you know the counts that you would see, you would measure over a dry patch of regolith. So the equator of the moon would be a good place for that. And so we'll make that measurement as we're flying into the South Pole. Right when we get over, we'll still be over the lunar highlands. It'll be dry, and we'll have a nice dry count rate. And then every count rate that we measure over the pole, where there are these putative hydrated regions, will just be with respect to the dry count rate. And so as long as from one measurement to the next, the instrument responds the same way, or we can make a correction for it, we don't even necessarily need to have an absolute calibration. But that's only a function of the fact that we're like the third neutron instrument to fly to the moon. So we can take advantage of the previous measurements. So
that's really cool. and very useful for you guys too.
Yeah, it's nice to be third.
Yeah. Yeah, sometimes being groundbreaking isn't it's not always the best thing.
Yeah.
So you guys have been working on this for, oh my gosh, how long has it been? 5 years? No, it's longer than 5 years.
Well, if by working on it you mean like when did I write the proposal for it? That was about 7 years ago.
Okay.
Like how long have we had physical like flight hardware? Probably the past maybe 3 years ago, something like that was when we started to get hardware.
Mm-hmm. Yeah. So in that, well, I guess we'll say 7-year timeline, what have been some of the most notable lessons that you've taken away from everything that's gone into LunaH-Map?
Oh boy.
Sorry, that's like I feel that's always like the worst question I think that I ask people. It's like, oh, you know, just what is everything in your head?
I've learned so many. I mean, when I wrote the proposal, to go back that far, like I was a postdoc at ASU. I had been involved in missions, you know, Mars missions. So I'd seen the science implementation of missions, but I hadn't really seen how things come together. worked on science image targeting for the Mars Reconnaissance Orbiter. So I'd kind of seen a little bit of like orbital planning, orbital mission planning, but by no means did I have any business proposing this kind of thing, like a whole mission. And so I'm not sure what I thought I was doing, but I know I said at the time that, you know, this seemed like a cool opportunity. I had this idea that I took, you know, that seemed like an idea that was worth scientifically pursuing. And I think I thought I would just learn something. And I think I said that even at the time. I was like, I'll write this proposal and I'll just see if I can even write it. You know, like, can I even write the thing? And that was a huge struggle. I mean, I think I'm not even sure if there's a lesson in here, but I know several times throughout the process, I could see how complex putting a mission together actually was. I mean, I think I maybe knew that it was complex, but I'm not sure that I had appreciated how complex it was. I think I thought, well, you know, yeah, of course you need to solve the, you know, you have to get a trajectory solution, but it's probably just, you know, you could plug it into a program or you could do some n-body simulations. Like, I don't know, typical like white male majored in physics guy. I was just like, oh yeah, you know, you just approximate it, you could figure it out. I was just doing really dumb stuff. And then over the course of writing it, I realized like, wow, you need a huge team of people to like pull this off. And I realized the complexity of it and why missions at JPL and NASA centers, I mean, they have teams of people that bring things up to the PI, right? The PI is like, oh, you know, tell me what you've decided or what the options are, option A, B, or C. Like, I was just, you know, deciding, and I recognized that I shouldn't be doing that. Like, I should have somebody telling me if this was correct, who knew orbital dynamics or who knew various elements of engineering a spacecraft. Or, you know, I was spending a lot of time with the instrument folks and talking to the trajectory folks and trying to make sure that the mission closed scientifically. But there were all these other elements that I was trying to bring together: budget, schedule. I mean, the reason I'm telling you this is I asked my boss at the time several times, like, hey, could I just stop writing this? Like, this is so crazy. Could I stop? Would you like tell me to stop? and it's the weirdest thing to hear. Like, I don't know why I didn't just stop, but I wanted somebody to tell me to stop. And he was like, well, tell me why is there some specific reason? And I was like, I kind of told him some version of what I just told you. I was like, it's too complicated. It's hard. I don't know what I'm doing. Like, I'm not sure that this is working. And he's like, well, I'm not hearing anything that says you can't do it. I'm like, yeah, I mean, I guess. Like, I mean, it just seems like I'm going to miss something, you know? Like, I don't know. And he's like, oh, yeah, but why not just give it a shot, right? He's like, I'm not seeing a definite reason why you shouldn't do it. I'm like, okay, so I'm going to keep working on it. I asked at least 2 or 3 times if I could get permission to stop working on it. And I don't know, there's some lesson in there probably that I learned that I'm way too persistent or something, or maybe there's some value in being persistent. I don't know, but I think the other thing that I definitely, you know, I learned it at the proposal phase, and I honestly thought I would never, that was fun. I had success that I submitted it. But in the implementation of it, I mean, I embraced that element that I learned during the proposal wholeheartedly. Like, I felt like I had to say, I don't know. I am not the expert. This is my team. They are the experts. You guys tell me what the right thing to do here is, right? I mean, it was very much a deference to all of the various elements of expertise. Like, we worked with a company, like I was telling you, in Boston, that made the detectors. They make a lot of detectors. So, you know, they would ask me questions, oh, is this okay? I'm like, this is, you know, your domain. Like, even though it's a science instrument, I was very deferent to like how much the team members individually were bringing in their experience, that I just, you know, I wasn't gonna push them around or tell them, you know, this isn't the right thing to do. So I think at the end of the day, LunaMap feels like a collaborative, like it's very much like everyone put their own piece of themselves into it, as opposed to like me just telling people what to do. Like, it's no, like it was out of necessity, and because it had to, like there's no other way, like it had to really be a product of everybody that worked on it contributing their own expertise and knowledge to it. So I don't know if that's maybe the thing that I took with me, like on a daily basis throughout the mission, was just like, you know, telling myself when I get in the office, you don't know, and reminding myself, like, I don't know nuclear physics. I do not know navigation and trajectory for spacecraft. I do not know thermal design. You know, like, what do I know? Like, I got a PhD in geology. I know space rocks. You know, like I can do neutron spectroscopy of space rocks and modeling and simulations of, you know, all, and like I know what I know, and I got my PhD in it, but like I will defer to the experts, which I am not in all these other things. And I think that wound up being a, you know, maybe probably frustrating for people sometimes, because I refuse to make a decision about certain stuff. I would just want them to make the decision, because I don't want to. But sometimes I would just come in and do it. Anyway, I'm sure it was frustrating for people. But I think in the end, everybody got to feel like LunaMap is theirs, and, you know, the people that worked on it. So that's one of probably many lessons I had to learn. I learned a lot about, you know, what being small means too. Like, you know, as a CubeSat, like I'm sure you felt this on maybe in some version of it on Phoenix. Like, there's no reason. Well, there is a reason. Why is LunaMap the way it is, right? Like, why do we have all of the struggles that we had in our program? Why would Phoenix have all the struggles it had? What could solve those struggles? I'm guessing money, right? Like, if we had given you more money on Phoenix, right? Like, that could solve a lot of the problems. It's not the only thing that can solve problems, but like, honestly, like you can get people with, you know, you can pay people for their time. And so I found that, you know, understanding where LunaMap fits in the overall scope of things that NASA is doing and why it's doing it. Like, I feel very strongly that the data we're going to collect is important, obviously. But I had to recognize, like, step back and say, like, okay, but what is this mission to everybody else? You know, when I'm arguing to increase our budget, which I did several times, I had to recognize, like, what this means to the people I'm asking the money of, and where LunaMap fits in the overall landscape of missions was important. And I think as a lesson, like, that's the thing that I also now take with me moving forward, is like, you know, I'm glad, you know, LunaMap is an experiment, just like Phoenix was an experiment, just like any other mission is an experiment. But NASA knows how to run the experiment for class A, B, C, D missions. Like, that experiment is still, they're all still their own experiments, but they know how to run them really well. LunaMap, and probably to some degree Phoenix, is its own unique snowflake of an experience. There aren't any other experiences to draw from. So I feel like, you know, if LunaMap is successful, or any of these other, you know, dozens of CubeSats on Artemis 1, or any other, you know, student-led space CubeSat that's successful, like any of these missions that delivers a spacecraft and executes a mission, we've learned something that we need to take with us. You know, like in my case, I hope that NASA can learn that there's something valuable that can be gained from these missions at this, you know, this between 10 and $20 million, right? Like, very, very low money for NASA missions. In the world of, you know, NASA high dollar, you know, missions, like, that's not very much. And so I think, you know, as a proof of concept for like future like Star Wars probe droids type thing, things
Right.
things that NASA would ride along on any mission they're sending to anywhere in the solar system. Hey, what's some really cool, high risk, high reward data that we could collect at this place or along the way that we would never ever collect with the primary spacecraft, right? Like that's, I think, the sweet spot for this stuff, because it's like if you pick something like that, you're always gonna take a low budget profile. You're never gonna spend a lot of money on something like that, and so the high risk comes from that, and so it all flows naturally, and everybody understands what it is. And you don't get these questions. Sometimes people just ask me questions about LunaMap, like acting like it was a Class A mission or something. Like, didn't you go through this gate review? It's like, no, that's not what this is. Like, this isn't that experiment. This is a different experiment. And so I guess I treat them, that's like, I don't know if that's a lesson, but it was important for me at the time and I spent a lot of like time in my office with the door closed and just like thinking like, what am I doing, right? Like, what is this? Like, what am I trying to do? Because at the end of the day, I recognized like, well, if I just had 200 million more dollars, we could, easily do this, right? Like, and it's like, but that's just a thing, 200 million more dollars, right? That you could easily go get that if I was any other NASA mission. And so it's not a question of whether or not the science is good or not. It's not a question of whether or not, the heat island data that Phoenix is going to collect is meaningful or not. It is. That wasn't the question NASA is asking by running that experiment. They're asking a different, they want, did you guys learn something really cool and valuable in the process of building Phoenix? I think the answer is unarguably yes, right? Like, that was a good experience for the students that did it. And so, yes, we should do more of those, like, regardless of the ultimate outcome. But if you get the urban heat island data, that's awesome. That's valuable data that we need to get. And LunaMap just sits in a different landscape of experiments. And anyway, that's how I, got to sleep at night, I guess, working on this thing. Because I did have to ask for money, and I had to, ask. There were points at which, I was asking and saying, you don't have to give us additional money. But this is what we can achieve with the current amount of money that we have. And there were versions of that where we were going to turn LunaMap into something much more like Phoenix, where it's like, okay, this is what the mission looks like in this mission, this experiment. And if that's what NASA decided, I was going to be completely fine with that, right? Like, that's not for me to decide. That's for NASA to decide. And I just gave them those options, and they just kept choosing, some middle of the road option. Like, they never chose the high dollar option, and they never chose the lowest one. They chose something in the middle, and they asked if I could make that work. And yeah, like, we always could. But yeah, anyway, that's, I guess, that's the thing that I take with me each day, I guess, is just, if I go work on some other mission in the future, like, the privilege that scientists have to work on like a Class A mission. Oh my goodness. Like, just to like walk into the room and be like, yeah, of course I'm going to get my science data, and it's going to be great, and the instrument's all calibrated, and I'm just going to write some science papers, and that's awesome. Like, I would love to get to that point someday. And I mean, now when I look at these big missions, that's kind of how I view them. I'm like, oh wow, somebody else is doing all that hard work, like, to make this thing go. Like, and I could come in and look at some neutron data and do some science. That's wonderful. Like, so yeah, an appreciation for these, just how hard these things are to do. Like, it's really hard. Like I said, I can't believe what a naive idiot I was thinking I could just like do this from my postdoc office. I don't know what I was thinking, but I think it has something to do with being a white male physics major, I'm sure.
Oh, I mean, heck, when we started Phoenix, like, we didn't know what we were getting ourselves into. We're like, oh, we'll make a CubeSat, and you just buy all these off-the-shelf components and put them together, and it works, and then you launch it. It's like, like, we had no idea how complex Phoenix really was when we wrote the proposal. We didn't think about calibration. Even just the data itself that we wanted to collect was de-scoped just for time's sake. Because at the end of the day, the goal with our NASA grant was, I mean, if you got science, like you were saying, it's exactly like you were saying. If you got science, it's great, but the primary goal was for it to be educational and for us to learn more about what it takes to put a functional system together, as opposed to making a system that's 100% perfect and gets all the science data that we wanted. And so we had to make a lot of trade-offs as we did that to get there. So and then there was, I mean, kind of in the larger scope of things, because we had a launch date and then we couldn't make that date, and we had to propose to be scrubbed and get a new contract for a launch. And that was really scary because we didn't, know what NASA was going to say. But at the end of the day, it's, it's like you were saying, they want you to learn something, they want you to finish it. And so it's time and money, and they don't prefer that you do that. But we were very grateful that they did do that for us. So we actually did get to finish that experience the way that we were supposed to.
I think, I mean, that reminds me of talking. I talked to Phil Christensen at some point early on, and when we were, and by the way, we faced several, if not many, various times when we were almost canceled. So it's it's I think a rite of passage, probably, just to face cancellation at least a dozen. I don't know how many times. Way too many, I think, for us. But anyway, I was talking to Phil about him. I remember he was very skeptical, rightfully, of the initial budget, and I didn't know anything at the time, and I remember saying, well, I was like, why do we need so much money to do? Because I just didn't know. I had no basis of understanding, and I don't think what I remember him saying was something like, I don't think you could send a brick into space for like less than $5 million. And I think, I don't want to say I disagree, but there's an element of that I think you can send a brick. You just won't know that the brick won't fall apart as you launch, or you won't know that the brick's going to survive. Like, this is the nuance of it is, I think, more where LunaMap lives, which is like, can you build, like, I mean, we weren't even sure that we could build it, but like at this point, we built it, we delivered it, we tested it. So we showed that you can, in fact, build a spacecraft for around $15 million, right? And we can test it, and it can potentially operate in these environments. So it's not a question of can it be built. Now you're in some other world of how sure can you be that it's going to do what you think it's going to do, right? Mm-hmm. And that is the dollar amount that you can put on that is infinite, I think. And you'll never get to 100% certainty that your brick is going to be a brick after you launch, and your brick's not going to fall apart, and your brick's going to do brick things when it gets into space. I mean, it's like, I think that's the like weird kind of realm that nobody, unless they do these types of things, knows what happens. It's like, and there's all a bunch of things that reduce risk and generate more mission assurance. And that's all there is between, in my opinion, $15 to $20 million and $800 million later, you're at a mission that's, it's larger. And you have two flight models, you have two engineering models, you've got, all these test protocols and procedures, you've got all these subsystems that have been tested at integrated level, you've got teams of document review, like, okay, you've got all that stuff, and that's great. I mean, I'm not saying that to say it's bad. I'm just saying I think we need missions like that. And if we're at a national level, if we're going to go to Europa, like, yes, like, make sure that stuff's going to work. Like, but there's this other class of things that I think should exist, like where we don't do all that stuff and we just take risks. And I feel like I'm so like just grateful for the missions that have come before that enabled us to even do LunaMap, right? Like missions like Phoenix that are just like students developing technologies and testing them, and then some of them don't work, but they test them and they keep testing them. It's like 20 years of CubeSat technology at this point that we get to just put together into LunaMap. And so in the case of Phoenix, now you guys have an IR camera, right, that has been into space. I know that there probably have been like defense ones or something, but not for the stuff that normal people can use. So we could potentially think about testing more small IR cameras on deep space CubeSat payloads and things like that. So I feel like we have to keep doing these things at these levels and then incrementally figuring out how they slot into the bigger picture for exploration, because I think they do have a role. And the only other thing I'll say is, like, NASA, since LunaMap, they still have calls for these SmallSats in quotes. They're now like the size of 2 refrigerators. The cost cap is like $60 to $80 million. Like, they're still small in the scope of NASA missions, but they're no longer, they're following the gate reviews, the more rigorous. They're following a more of what's called like a Class D mission structure. And that's good too for the things that I'm not saying anything against those. I just think that these little things these high risk things should exist. And I think they should leverage, the technologies that come from student run, or company run, whatever, just stuff that's being demonstrated in the community, and has been demonstrated before that we can implement in these high risk missions for planetary.
Yeah, I remember even like when we first started Phoenix in 2015, like a lot of, some people were telling us like, a lot of teams build these CubeSats and they launch them and they don't work. And if you look at, I think there was a paper that was studying like the failure rates of CubeSats very early on compared to the later years. And early on, a lot of them didn't really work. And it's because, exactly like you're saying, they were willing to take risks and try this process out. And through that, now you have places like Cal Poly that's developing these all the time. And they, you have a lot of students who go through that and they learn how to make a CubeSat, and then they translate that to a lot of these larger and more complex missions that are doing amazing things. Like, Perseverance rover, the Ingenuity helicopter, all that stuff comes from those risks.
Yes, so I agree. Yeah, and actually, Ingenuity is a great example of it's this thing that kind of nobody was sure if it was going to work. Like, wasn't essential to the Mars 2020 Perseverance mission, but super cool. I mean, it's an enabling technology that now that they've demonstrated it works, they could think about implementing that into the mission profile for some future mission where you have a helicopter scouting the terrain that the rover can't see, and actually getting some information and digital terrain models that feed back to the they could use to implement new drive strategies or places to go. I mean, we'll put a neutron detector on one. I mean, I'm speaking out of turn, but stuff like that. I think that's exactly the right type of kind of bold risks that people get excited about. So I think, I don't know what the right term is. Space dinghies, like probe droids. Like I'm not sure, but it's something that gets the spirit of what it is. But
I think that's why a lot of people, connect with things like Voyager or Apollos, because it was the first time we were doing a lot of those. And even then, it's like 1960s, 1970s technology, and like look at all the cool stuff we were able to enable with that. So it's But I think there's no better way to end this podcast. I know it's kind of funny. I said we wouldn't go until 3, and here we are. But thank you so much for doing this with me. This was a lot of fun, and it was so great to learn about LunaMap. And I'm over the moon, no pun intended, for you guys to launch and operate. So, congrats.
Well, thanks for having me on. It's good talking to you.
You as well. And and that's all for this episode of The Art of Space Engineering. Thank you all again so much for tuning in. I try to post new content as often as I can and make episodes that are useful to you and give you a better insight into how space missions come together in general. That being said, if you have any comments, questions, or ideas for future episodes, please feel free to shoot me an email or connect with me on LinkedIn. And you can find both of those resources in the show description. If you've been enjoying this podcast and you want to support it, please share these episodes with your friends who might be interested in them. And don't forget to follow this on your favorite podcast source and on Facebook to get notifications on upcoming episodes. Here's looking forward to future adventures and the lessons learned from them. Cheers, Sarah.